We have already discussed three intervals in previous modules: the semitone, the whole tone, and the octave. These intervals helped us in our building of diatonic scales. This module continues the discussion of the remainder of interval possibilities. All intervals are given two descriptors: a number that represents the general diatonic size of the interval and a quality. The general diatonic size refers to the number of distinct pitches contained in the interval. For example, the interval from C to D contains two pitches, C and D. So we call this interval a second. From E up to B, there are 5 pitches. So we call this interval a fifth. On the staff, the general diatonic interval is represented by the number of lines and spaces contained within the interval. The possible general diatonic size of an interval can range from having no distance, which is called a unison, up to an infinite distance, but we generally stop at the 12th. When finding the general interval size, the use of accidentals does not change the general size of the interval. The distance between C and D flat is still a second. Even though it is a smaller type of second, there are still 2 pitches contained in the interval. The second descriptor, the quality, tells us specifically about the number of semitones contained in an interval. Interval qualities can be perfect, major, minor, augmented, or diminished. Perfect intervals are intervals in which the frequencies of the 2 pitches are related to one another by a superparticular ratio. A superparticular ratio is a ratio in which the greater term exceeds the lesser term by 1 unit. This all goes back to the Greeks. The Greeks were trying to determine the best way in which to build a scale. To their ears, the notes that sounded the nicest when played together were those with superparticular ratios, and those ratios were all created by the division of a string. This is a simple diagram of a monochord. It is a one-stringed instrument used solely for the purpose of demonstrating musical mathematical ratios. If we play the open string, it sounds like this. If we find the exact midpoint of the string and put a bridge at that point, and then play 1/2 of the divided string, we will get a pitch that is exactly 1 octave higher than the original open string. If we relate this to frequency, the higher note has a frequency that is exactly double that of the open string. The ratio for the octave is 2 to 1. That is, if we divide the string into the proportion of 2 equal parts and play only one of those parts, it will sound 1 octave higher than the undivided string. In terms of interval identification, the octave is called a perfect eighth, or P8 for short. There are 8 pitches contained in the interval, and the quality is perfect. If we look at a major scale, there is a naturally occurring perfect octave between the tonic at the bottom of the scale and the tonic at the top of the scale. They are both scale degree 1, or Do. They are just 1 octave apart. There are 3 more perfect intervals. A unison is perfect because it is equal to itself. There is no discord between a note and itself. A fifth is also perfect. Its superparticular ratio is 3 to 2. If we return to the monochord, and this time divide it into 3 equal parts, and place a bridge on one of those nodes, and play the side of the string that is equal to 2 of the 3 equal parts, we will get a pitch that is 1/5 higher. Here's what the open string sounds like again. And here's what the perfect fifth above sounds like. On a major scale, there are several naturally occurring perfect fifths, but the one we most commonly associate with the perfect fifth is the interval between Do and Sol. The final perfect interval is the fourth. Its superparticular ratio is 4 to 3. If we divide the monochord string into 4 equal parts, and then play the length of string that is equal to 3 of those parts, we will hear the perfect fourth. Here's what the open string sounds like, and here is what the perfect fourth above sounds like. On a major scale, there are several naturally occurring perfect fourths, but the one we most commonly associate with the perfect fourth is the interval between do and fa. We can't very well carry around a monochord with us to determine perfect intervals, so another method that has been developed to determine interval quality is to memorize the number of semitones in each interval. This is possible because of the equal division of the octave that you learned about in Module 7. In a perfect unison, or P1, there are 0 semitones. There is no distance between a note and itself. In a perfect fourth, there are 5 semitones. In a perfect fifth, there are 7 semitones. And in a perfect octave, there are 12 semitones. Major and minor intervals are named by how they occur in both the major and natural minor scales. These intervals do not have superparticular ratios. If we look at a major scale, we identify the interval from scale degree 1 up to scale degree 2 as a major second. There are 2 pitches contained in the interval and 2 semitones. We have previously referred to this interval as a whole tone. A major second and a whole tone are the same interval. We identify the interval from scale degree 1 to scale degree 3 as a major third. There are 3 pitches contained in the interval and 4 semitones. We identify the interval from scale degree 1 to scale degree 6 as a major sixth. There are 6 pitches contained in the interval and 9 semitones. We identify the interval from scale degree 1 to scale degree 7 as a major seventh. There are 7 pitches contained in the interval and 11 semitones. We can replicate the same process on a natural minor scale. Note that the intervals from the tonic to the unison, fourth, fifth, and octave are still perfect. In both the major and minor modes, these intervals remain perfect. Scale degree 1 to scale degree 2 is still a major second in the minor mode. We identify the interval from do to me as a minor third. There are 3 pitches contained in the interval and 3 semitones. We identify the interval from do to lay as a minor sixth. There are 6 pitches contained in the interval and 8 semitones. We identify the interval between do and te as a minor seventh. There are 7 pitches contained in the interval and 10 semitones. There is only one major minor or perfect interval that this prosent hasn't revealed, the minor second. The minor second is equal to a semitone, and we've already shown it in a previous module that they naturally occur between mi and fa and ti and do in the major scale. The minor second has 2 pitches contained in the interval and 1 semitone. We've used the examples of the major and minor modes to show you how each of these intervals naturally occurs in the diatonic system, but it is possible to build any type of interval beginning on any pitch. Here is a handy method for notating a given interval on the staff. Step 1. Notate the first pitch of the interval. For this example, let's use E, and let's build a perfect fourth above E. Step 2. Counting the first pitch of the interval as 1, count up the lines and spaces until you get to the general interval size that you need. We need some type of fourth here, so we have to count to 4. 1, 2, 3, 4. Place a note head here. Step 3. Using the keyboard, either actual or visualized, start from the first pitch and count semitones until you get to the number that you need. In this case, we need 5 semitones to create a perfect fourth. 1, 2, 3, 4, 5. That gets us to A, and no accidentals are needed. We have successfully written a perfect fourth above E. Here is what it sounds like. We can write intervals both above or below a given pitch. Let's write a minor seventh below the pitch G sharp. Step 1. Notate the pitch G sharp. Step 2. Counting G sharp as 1, count the lines and spaces from G sharp until we get to the general interval size of a seventh. 1, 2, 3, 4, 5, 6, 7. That places us on some kind of A. Step 3. Using a keyboard and starting from the given pitch, count semitones until you get to the number that you need for the required interval. In this case, we need 10 semitones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That places us on a black note on the keyboard. Because of step 2, we know that we need some kind of A, and now that we have counted semitones, we know that we need to add a sharp to the A to get the correct pitch indicated on the piano. Step 4, add that accidental on the staff. We have now written the pitch that is a minor seventh below G sharp. Here's what it sounds like. The pitches of an interval can be played melodically, one at a time, or harmonically, both together at the same time. Intervals that are 1 octave or smaller are referred to as simple intervals. Intervals larger than an octave are called compound intervals. It's not uncommon to count general interval sizes up to a 12th, but often we'll switch to using compound intervals once we get much larger than a 10th. So instead of saying that this interval is a minor 10th, we can say that it is a compound minor third. That is, the higher pitch is 1 octave plus a minor third higher than the lower pitch. Instead of saying that this interval is a major 13th, we can call it a compound major sixth, because the higher pitch is 1 octave plus a major sixth higher than the lower pitch. We can take any interval and make it larger or smaller. To make an interval larger is to augment it. To make an interval smaller is to diminish it. For example, let's look at the major second between C and D. It is a major second because there are 2 pitches contained in the interval and there are 2 semitones. If we add a sharp to the D, we have made the interval 1 semitone larger. There are still 2 pitches contained in the interval, some kind of C and some kind of D. But now there are 3 semitones. This is called an augmented second. We could also make the interval smaller by adding a flat to the D. It is still a second because there are 2 pitches contained in the interval, some kind of C and some kind of D. But now there is only 1 semitone. If we look back at our interval chart, we see that the interval with 2 distinct pitches and 1 semitone is a minor second. In this case, we have changed a major second into a minor second by making it 1 semitone smaller. If we double flat the D, this is still a second, but now there are 0 semitones. This is now a diminished second. We have made it 1 semitone smaller. Intervals can have enharmonic equivalents. This means that 2 intervals will sound the same, but be written differently on the staff. An augmented second is enharmonically the same as a minor third. The difference is how the intervals are written on the staff. If a perfect or major interval is made 1 semitone larger without changing the general interval size, it becomes augmented. If a perfect or minor interval is made 1 semitone smaller without changing the general interval size, it becomes diminished. In the Middle Ages, augmented and diminished intervals were to be avoided. They were considered unpleasing to the ear and difficult to sing. One interval in particular, the augmented fourth, and harmonically the diminished fifth, was known as the Diabolus in Musica, or the devil in music, because it was so discordant. Today, we often refer to this interval as the tritone, because it spans the distance of 3 whole tones. The tritone can be spelled as either an augmented fourth or a diminished fifth on the staff, but it will always contain 6 semitones. The tritone occurs naturally in the major scale between Fa and Ti. Practice writing all sorts of intervals. Build them using staff paper as well as at the keyboard. Play around with turning perfect, minor, and major intervals into augmented and diminished intervals. Become incredibly familiar with the number of semitones that exist in each simple interval. The identification of intervals will be important in the building of triads.